All right, now we'll get into a formal ANOVA test. So pretty much what we've done is set up the test statistic for the test. And so what we're saying here is that this F test statistic, this is what it's doing, this is how you interpret it. Okay, so we didn't provide formulas on how they do sum of squares for between and within groups, but really we should understand what this number is trying to tell us to do, all right, as far as looking at the previous box plots. But now what we want to focus on is, how do we get this p-value? Okay, so pretty much we've kind of talked about how we get all these numbers in the ANOVA table, but now it's, well, how do they find that p-value? So usually there's some conditions that need to be met here. Okay, so it just says this F statistic, it is random, and we need to find its sampling distribution like we did for sample mean and sample proportions. So what we need first is random sample and independent measurements. We need independent groups. We need to assume the same variance. Okay, the population variance or standard deviations of the groups are the same, right? And of course, too, is either we have a small data set within a group, but it's normally distributed, or the sample size is at least 25 within each group. As long as all four of these hold, we can assume that our F statistic follows something called an F distribution, right? So no surprise. We had the chi-squared statistic, which followed the chi-squared distribution, right? As long as these conditions were met. Now we introduce the F statistic. So just one thing to know, it's always positive, okay? Because we're looking at variation, so it's always positive. And these distributions require 2 degrees of freedom. So the degrees of freedom in the numerator, that's from, usually that's from the variation between, usually it's number of groups minus 1. And the degrees of freedom of the denominator, well, that's equal to the degrees of freedom of the within, okay, the sample size minus the number of groups. Okay, but it looks kind of like a chi-square. It's definitely something that's unimodal and skewed to the right. Okay, so just one thing is that if any of these things are violated, we need to be careful here. Okay, so number one, probably the most which is the most important out of all four of these, and most important out of all the tests that we've seen. But it says, yeah, of course it violated, it could introduce bias into the data, right? So one thing to note is, like, if group were a family and sampled within family, this obviously would not be independent. Okay, there could be some dependency between a family or within a family. Okay, independent groups. So a violation of this would be, well, suppose the same subject received 3 different medications and the doctor recorded the result of all 3 from the same subject, right? So the fact that, so we have 3 groups, okay, we have a categorical variable, which is the type of medicine, right? 3 groups. So we're saying within each group, they should be independent. But in this example here, we do have 3 groups, but the same person is in each group, right? It's the same subject. So in this case, they're not independent groups, right? And what we call, and this type of study is not uncommon. Okay, it's called something called repeated measures. Okay, the other thing we need is same variance. Okay, same variance, homoscedasticity. Okay, so it's just saying that the population variances or standard deviations of the groups are the same. Okay, the largest standard deviation. So the key thing there is, the ANOVA, we could look at the box plots, that's one key indication, or dot plots, but also ANOVA table gives us the summary statistics. It gives you the sample standard deviation within each group, so we have to compare those. Okay, so it's just saying the largest standard deviation is no more than twice the smallest. That's usually the rule. Anything more than that, we should be careful, but that's just one of the requirements needed for us to use this distribution. Right, and of course here, normal distribution or large sample says the distribution of observation is normal in each group's population, or the sample size is large at least 25. So here's saying check residuals, and we need an F distribution. Okay, so just to kind of go back to the output here of our original example, right? So now we're saying, well, okay, now we can look at everything now. So first thing is we look at sample size within each group. Okay, 34, 16, 83, 120. Right, so all of these are greater than or equal to 25 with the exception to 16. Right, so we have to safely assume that the population of sleep within the heavy alcohol users, that this comes from a normal distribution. Right, so one thing we can do is look at the residual plot. Okay, that's what the residual plot does. So if I were to look here and look at these residual plot, well, ooh, nice. It looks unimodal, symmetric, and looks like a normal distribution. Right. So as far as checking whether or not something's normal distribution, we look at this distribution of these residuals, and really because it's sum of squares, right? So really square of differences, and so that's what we're saying, that these are pretty normal. So it checks out. Okay, it checks out. So we had a small sample size, but you have to verify. If it's small sample size, you have to verify that a normal distribution is safe to assume. Okay, so the other thing that we look at here, of course, we can look at the means, right? See, they're all kind of close to each other. Abstain had the largest, heavy had the smallest on average, right? So, and then standard deviations here, right? So we get into one of the assumptions that the standard deviations have to be the same. Okay, this here says same variance for each one. Okay, so remember, standard deviation is just the square root of it. Okay, so what we're just saying here is that, well, that's 1.28, 1.29, 1.15, 1.5. They're definitely pretty close to each other. Okay, so we'd be pretty safe here. Okay, remember standard error is a little different. Standard error is standard deviation divided by the square root of n. Okay, that's how they got that number. So this is like the typical difference we should see between the sample mean and the mean within the abstain group. Okay, this would be the typical difference we see between the sample mean and the true mean within the heavy group. Okay, when we check these out, everything looks okay. All right. So we could check these things. As far as independence, that's kind of harder to check. Random sample, it's harder to check. It just depends. You know, at the follow-up, say, how did you collect the data? And let's look at who's in your data, just to make sure. Let's check the design of your experiment to make sure everything runs smoothly there. Okay, but as long as all of those hold, then what we could do is find our p-value, right? And that's what this is about. We could find our p-value. So we wanted to test whether the amount of weekend sleep is associated with reported alcohol use, okay, which is categorical. We want to test it at a significance level of 10%, right? So what this really means is that, well, if they're not associated, right, if numeric and categorical are not associated, it means the mean numbers of sleep, hours of sleep, they're the same for each group, okay, versus the alternative that at least one mean is different. Okay, so we calculate our F statistic, which is variation between groups over variation within groups, and we get 2.14. So this tells us the variability between groups was 2.4 times greater than the variability within groups. So in this case, our p-value was 0.0594. So pretty much what they did is they found the probability of observing 2.14 and larger values, assuming that the null hypothesis is true. And the way they did this was by using the F distribution, right? So here it's saying since p-value is less than alpha, we reject the null hypothesis. At 10% level significance, there is enough evidence to conclude there's at least one difference in the mean amount of sleep. Okay, so if we reject the null hypothesis, we conclude that at least one mean is different, but which one? All right, which one? Right? So we reject the null, but we can't really conclude much. Right? We can't really conclude much. I mean, so what we need to do is, if we reject the null, there's some other procedures that we can do to further analyze the difference in the means. So these procedures are done after the Anova, only if you reject the null hypothesis. Okay, if you fail to reject the null hypothesis, then we just end it there, conclude, hey, not enough evidence. It seems like there's no association between these two variables. Okay, but if we do reject the null, then how are they associated? Okay, meaning, is it given heavy? What does that tell us? Given a heavy alcohol user, what does that tell us about average number of sleep versus someone who does not drink? Okay, so that's what we want to get into. So last time we introduced, right, we talked about this overall significance level. So we still have it here. Okay, it says we wish to determine which groups have different means from other groups. Right, and it says an appropriate correction must be made in order to keep overall significance level at a specified value. So it's just saying, hey, after we do the ANOVA, now we're going to do this multiple comparison again, just like we did before with the Bonferroni intervals, right? But we're going to use a different method. Okay, so this is called the Tukey honesty significantly difference confidence intervals. So I'm just going to say these are the intervals that we use. As far as for Bonferroni, it was pretty obvious how we made the adjustment there for the overall significance level, right? I mean, all we did was, divide by the number of comparisons, And it is a slick, just crude, quick approach, but, it doesn't work well for a large number of comparisons. So Tukey does much better with that respect, but I'm not going to get into how they derive it because now we get into mathematical statistics. Bonferroni has some intuition behind it, but with Tukey it's a little bit more mathematical. So we're just going to say, hey, look, if we're doing post hoc and we want to do multiple comparisons just like how we did with Bonferroni, we will, but we're going to use Tukey's method. Okay, so here it says, of course, we use this only if we reject the null hypothesis. Okay, so the nice thing is, remember when I was working with Bonferroni, I had to use StatCrunch where function to get all the different comparisons, and it was really, for StatCrunch, a lot of work to do. The nice thing within StatCrunch is it already has a built-in multiple comparison confidence intervals for the Tukey interval. So I don't have to go and keep track of all the comparisons. StatCrunch will do that for me. Okay, and let me just show you very quickly how that's done. Okay, so if I were to revisit this sleep study here, okay, where I created my ANOVA, well, I don't have to close it. I can just go to options and edit. Okay, and by the way, this is where I did my dot plot, histogram of residuals. Okay, and then I could do here compute Tukey, and we could do 90%, I guess, 90%. Okay, we could use any one. Maybe I could use, I'll show you a different one, 95%. Okay, but if I just hit this here, there we go. So what it's going to give me automatically is this is what I had before, my summary stats and my ANOVA table results. All right, and then it's going to go ahead and give me the Tukey results. Okay, so here are all, so automatically it tells you 95% overall confidence level or capture rate, right? And then it tells you abstain subtracted from heavy. So it's abstain minus heavy, abstain minus light, abstain minus moderate. All right, this is saying heavy subtracted from light. So this is heavy minus light, heavy minus moderate. So we're doing the difference in the means. Okay, and then this is light subtracted from moderate. So all of these here, so lower and upper, they're all confidence intervals for the difference in the means. Okay, and all these are two sample independent T confidence intervals that we did before in chapter 9. And what these p-values are doing, these p-values are testing whether the differences are 0 or not. So they're doing two-sided hypothesis test for the difference in means of independent populations. Okay, so they're testing whether the difference is equal to 0 or whether it's not equal to 0. So this is a two-sided test. Right, so last time I had to do all this by hand in StatCrunch, more or less. And I purposefully left out the light category because I didn't want to do all these comparisons, right? So I just did like a three-way comparison, right? But you see in StatCrunch, it's nice and laid out for us, okay? But just remember, this is the estimated difference, right? This is like sample mean 1 minus sample mean abstain minus sample mean heavy. This is sample mean abstain minus sample mean light. This is sample mean abstain minus sample mean moderate, right? And these are the 95% confidence intervals this is the 95% this is the confidence interval for they're actually 95%, but because of the adjustments here, but this is the confidence interval for abstain minus heavy. This is the confidence interval for abstain minus light. This is the confidence interval for abstain minus moderate, right? And so that's how we read that there. And all they are just all our 2 sample independent hypothesis tests that we saw in 9.4 and 9.5. Okay, but pretty nice. And then also when I click those other options, right, we get like you get a dot plot here, and then you get a plot of residuals here as well that we used before. But what's kind of neat about this plot is that this is the overall mean, right? The grand mean is the average of all of these numbers, right? So we want to know if whether this mean, right? Let's look at the mean of weekend sleep, the mean of heavy sleep, the mean of light sleep, the mean of moderate sleep. And what we want to know is that are these 4 means kind of significantly different than this grand mean? Okay, that's another thing that we're doing in StatCrunch. Okay. All right, so very easy procedure here. We don't present how this Tukey interval was derived, but we're just saying, look, believe us. Okay, in practice, if you reject a null hypothesis for Anova, well, yeah, it's natural to want to know, well, where my differences lie. Okay, and so if I were to use this here in my interval, well, 0 is in all my intervals here. Okay, so there's nothing real exciting about this result, because upon further inspection, when I compare each of them, there's 0 in all of my intervals, right? So if 0 is in your interval, then we cannot conclude that there's a significant difference between these pairwise means. Okay, maybe there's some evidence here when we're doing abstain and heavy, okay, but we can't be too certain here. Okay, so not that much exciting results, but usually we're looking here, are they both negative or are they both positive, or do we have very small p-values, right? Those are going to indicate that this is where your differences lie. So as far as my smallest p-value, it's 0.2395. I mean, that's what we get there. Okay, so saying, look, well, actually from your original test, your p-value was 9%, 9%. So it was pretty large. So in here, we shouldn't be too surprised by this for now. Okay, so yeah, so that's all we have now for chapter 11. Next up will be chapter 12.